Welcome to Spring LIB.
Hey, my name is William, and today we're going to be working on a particle problem. So in today's problem, we have a positron and electron, each with 420 electron volts of kinetic energy colliding into each other, and they annihilate, and they form two photons, and we're trying to find out what the wavelengths of these two photons produced are. So how we're going to solve this problem is to use energy conservation. Energy of the first stage is equal to energy of the second stage. And we're going to have a couple of formulas to solve the first stage and solve the second stage. Some useful constants are going to be over here. So we have Planck's constant, speed of light, and we have the rest mass. The rest mass of the electron and the rest mass of the positron. They're going to be the same value because they have the same mass. They just have different charge. All right. So first things first, we're going to need to solve the first stage is E equals gamma mc squared, the relativistic energy. And we can rewrite this into a more useful form of this problem. Namely, we can write it as the rest mass energy, which is, I'm going to abbreviate as RME, plus the kinetic energy, which is given to us, KE. Okay, the rest mass energy is going to be Einstein's famous equation of E equals mc squared. Note that we have a gamma here because it's moving. This applies if it's at rest, right? So we have rest mass energy mc squared plus our given kinetic energy. And we know what m is, right? M is 0.511 MeV, or 511 eV per c squared. So 0.511 MeV, mega electron volts, over c squared times c squared. C squared above, c squared below, they cancel. And then the given 420 electron volts. Great. Okay, so electron volts, that's 10 to the 3. MeV, that's 10 to the 6 electron volts. So we're going to have 10 to the 6, 1, 2, 3, so 3 zeros, right? So 511,000 electron volts plus 420 times 1,000, because K, EV, and the result is going to be a big number, which is 511 plus 420. That's going to get us 931,000 electron volts. Okay, but this is per photon. Sorry, per particle. And so we have two particles, each with the same energies. So our E total in the first stage is equal to 2 times that many electron volts. Okay, great. So how do we find the wavelengths? Well, to find the wavelengths, we have the photon energy, E equals HF, which is also equal to E equals HC over lambda. And we know that C equals F lambda for light, just in general. So this is going to be the equation we use because it gives us the wavelength. So we have two photons, right? So E total 2 is equal to 2 of these, 2 times HC over lambda. And that's going to have to be equal to E total 1 through energy conservation, right? So 2 times this big number here. All right, cancel, cancel. We have lambda is equal to HC over 931,000 electron volts. And plugging in to our equation. We have the constants provided here, eV per second, and we also have the speed of light. So putting those in, we have 4.14 times 10 to the minus 15 eV seconds times the speed of light, 3 times 10 to the 8 meters per second. All of this is over the energy we found over here. So 931,000 electron volts. Let's check the units just for sanity. So electron volts cancel, seconds cancel. We end up with meters, so that's good. And we plug all of this into a calculator. Times 10 to the minus 15 times 3 times 10 to the 8, all over 931,000. That gets us 1.334 times 10 to the minus 12 meters. And that's our solution.